Hello and welcome. This is Chem 302, video number 3 from chapter 15, NMR spectroscopy. Some learning objectives for this video today. By the end of this video, you should be able to predict which proton environment in a compound will produce a proton NMR signal that is the most upfield or shielded versus the most downfield or deshielded. And then you should be able to rank the relative expected chemical shifts in alkanes, alkenes, alkyl halides, alcohols, and ethers. So these are all families of organic compounds that you saw in 301. We will add in some other families as we progress further in the textbook. And then lastly, you should be able to use the N+1 rule for predicting splitting patterns and using the appropriate term for describing a specific type of multiplicity. The problem set problems from the proton NMR problem set that you should be able to do include these, and I apologize if after video 2 you weren't able to do numbers 3 and 4 just yet. That was my mistake. So by the end of this video, you should be able to do those as well as these. So let's go ahead and get started talking about chemical shift and chemical shift values. So remember that we can abbreviate chemical shift using that delta symbol. The chemical shift is defined relative to the frequency of absorption to that reference TMS, tetramethylsilane, that I mentioned in the last video. It's measured in ppm, and you're going to be given a chemical shift table on any assessment, formal assessment that you have in the class. So this, you'll notice, looks a little different than the chemical shift table I showed you last time. It's shorter, and that's because I've taken off some of the families of organic compounds that we don't have to worry about for now. So we're going to use this one today so you get some practice with it, and later in the chapter we'll start talking about carbon NMR. But for today, this is what we're going to be using. And I've posted a copy of this handout in Learn for you to reference for your problem set problems. Okay, so having said that, now let me put this aside. Let's get started. So if you're dealing with a proton that's on an sp3 hybridized carbon atom, you're going to find that those are going to absorb the farthest upfield. So remember, upfield is to the right. They are going to be very shielded. Okay? And if we wanted to compare, so let's take a primary carbon. Okay, so here we've got primary carbon versus secondary. So here's our methyl group, here's our methylene group, and now let's have a methine group. Okay, so if we wanted to compare the proton signals generated by each of these, so each of these protons is attached to an sp3 hybridized carbon atom. Okay? We expect their signals to be the farthest upfield, but they're not all going to be identical to each other. So when you're comparing protons that are attached to an sp3 hybridized carbon atom, there's a general trend that we see with the, let's start with the methyl protons. These are going to tend to be the farthest upfield. They're going to be around about 0.9 ppm, okay, just under 1. And again, this is a primary carbon that these methyl protons are attached to. With the methylene protons, they're going to be shifted a little bit to the left, a little bit downfield relative to the methyl protons. These are going to tend to be around 1.2 ppm. And the methine protons over here, they're going to be a little bit farther downfield, around 1.7 ppm. Is it important for you to memorize these numbers? No. It is just important for you to learn this general trend here. So as we replace on an alkane a hydrogen with an alkyl group, the remaining protons attached to the carbon, their signal tends to be shifted a little bit downfield. Okay? So don't memorize these numbers. Remember again that you're going to have this table. And in fact, even on this table, you can see they've got primary alkyl. Okay, there's your methyl group with your methyl protons. There's your secondary alkyl. So there's your methylene carbon with the methylene protons, part of that CH2 group. And so notice how that chemical shift range shifts a little bit farther downfield, and so on. With the tertiary alkyl, that has your methine group, your methine proton there, and that's even farther downfield. Okay? All right. So moving on from hydrogens attached to an sp3 hybridized carbon atom, which by the way, it's useful. So I've gone ahead and drawn out here the axes for our proton NMR spectrum. And so you're going to, if we use this table to say like, well, where, if we lumped all of these together, where do we find them? Anywhere from 0.8 up to 1.8. So just under 1 to just below 2. So in this region here, right, if we were to kind of block it off, is where we see these proton signals appearing. Okay, so now we mentioned last time that as we add electron withdrawing groups, we're going to see, so let's start by adding, let's do this. So let's let X here be an electron withdrawing group, and I'll show that. I'll make this bond really polar, okay? And here we have our hydrogen that's attached to a carbon that's attached to an electron withdrawing group. When this occurs, we see that the proton feels less electron density around it, and so where it absorbs is going to be farther downfield. So what are examples of electron withdrawing groups? Well, you learned about alkyl halides last semester. So let's take a look at some examples of different alkyl halides. Here we've got 2 different alkyl halides, and here I'm just for comparison using methane. So this signal absorbs around 1 ppm, and again, you don't have to memorize that. You would put it in this range here, okay? And notice how close that is, the 0.9 that I've given you there. All right, so let's then take a look at these protons here and these protons here, and how are they going to absorb relative to these? Well, these both are attached to carbons with electron withdrawing groups, so they're going to absorb farther downfield. So we're going to have a bigger ppm for each of them. And now what's the difference between these two? Well, fluorine is the most electronegative atom, okay? And so we expect this to withdraw more electron density from these protons. We expect this to be the farthest downfield compared with this. And in fact, if you look at the NMR spectrum, the proton NMR spectrum for each of these, this absorption is at 4.3 ppm, and this one is at 3.1 ppm. Can you come up with these numbers out of your head? No, but the general trend here is very clear that you would expect these protons to absorb the farthest downfield in this series. These would be the farthest upfield, and these would be in the middle in terms of, not like literally in the middle, but between, somewhere between. Now, so let's take a look at our table. Since these are both alkyl halides, are these absorbances in the range that we expect? So for alkyl chlorides, they give 3.6 to 3.8 ppm. So let's take a look at that. We have 3.1 here. Okay. So does this mean that this has to be wrong? No. So this is a hard part for students often if they get an absorption that's slightly outside of the range given in the table. They're like, no, it's impossible. This is just meant to guide you. Don't have it lock things in stone. All right, and I don't even have alkyl fluorides on here, but we would expect it to be that range to be farther downfield relative to this. This goes up to 3.8, and we said this was 4.3, and again, that's because I took the proton NMR of the compound, and that's what it's reported as. So that looks good. Nothing strange there. Okay, so what else are we going to encounter? Let's take a look at vinylic protons next. So these are protons that are on an sp2 hybridized carbon atom. So these are going to be shifted downfield relative to hydrogens that are on an sp3 hybridized carbon atom. Why is that the case? So sp2 hybridized carbon atoms, you've got that. So let's look at an example here. Okay, of a, here we've got a geminal alkene. So in a double bond, you have one sigma bond and one pi bond. And the pi bond creates a magnetic field of its own. You can read about it in the textbook if you want more details. But the take-home message is because of that pi bond, hydrogens that are attached to an sp2 hybridized carbon atom are going to absorb at a higher frequency or farther downfield. So these guys, so another term for this, these are vinylic protons. Okay, protons that are attached to an sp2 hybridized carbon atom are vinylic. And if you have, like we see here, geminal protons, the range on your table is around 4.6 to 5.7 ppm. And if we look at, for example, let's make this different, R, H. Okay, if we looked at, so this is also a vinylic proton. This absorption range on your table is going to be listed slightly downfield of the other one. Let's see, what is that one? It is 5.2 to 5.7 ppm. Okay, all right. So you should start to practice using this information about these specific types of proton environments and where you expect those absorptions to be. So before I move on, let's just do an example of, let's take chloromethane and let's replace another hydrogen with a chlorine to look at what we expect to see happen to the chemical shift. So then CHCl3. Okay, so if I was to compare the chemical shifts of each of these protons, I would expect this one to be the farthest downfield and this one to be the farthest upfield and this one in between. And in fact, what these are, so I said, I think I gave you this one. This was the 3.1 ppm. And this one turns out to be 5.3 ppm. And this one is 7.3 ppm. And again, you're not going to come up with these numbers. Now, in some classes, they will give you formulas to estimate these numbers. I'm not going to ask you to do that. I'm asking you to just rank their chemical shifts here, and then to be able to use the chemical shift table. Okay. All right, so let's practice this a little bit now. So here we've got ethoxyethene, also known as ethyl vinyl ether, which is a really common starting material for organic synthesis. And let's go ahead and see if we can apply what we know so far about proton NMR for this compound. So when we talked about the 4 important characteristics of a proton NMR spectrum, number 1 is the number of signals. So you're going to notice I'm always asking you, like, how many proton NMR signals are there? Or how many absorptions do you see in the spectrum? So what I want to do is I'm going to take this, I'm going to redraw this because the way this is drawn here, it's kind of deceiving. I might accidentally think that these are both in the same electronic environment. So I'm going to just redraw this. Anytime you see a carbon-carbon double bond, I recommend that you draw out all of the bonds attached around that carbon-carbon double bond. Okay, does it matter here which one has the H, which one has the O? No, it doesn't. So do what you like there. Just pick one. CH2, CH3. Okay. So I've redrawn this. First thing I want to do is label how many proton NMR signals we expect to see. So how many proton environments are there? So I'm going to start here because I noticed the next question is about which one is the farthest upfield, which one is the farthest downfield. When I look at this, I see a methyl group, and right away, bam, I'm going, that is going to be the most upfield. Right away, I know that. Okay, so this I'm going to label as environment A. Okay. Here our methylene group is in a different environment than all the rest of the protons, so this is environment B. Here now I've got vinylic protons, right, attached to an sp2 hybridized carbon atom. So I have 1, call that HC, 2, 3 distinct environments here. Now, if you are scratching your head about this, stop and do the X replacement that we did last time to demonstrate this. So I've got 1, 2, 3, 4, 5 unique proton environments. Okay, and now I had already figured out which one is the farthest upfield. These protons are the most shielded, so this is going to absorb around 1-ish, I would guess. And here, if you wanted to pull out your table and say, okay, primary alkyl, that's a methyl group there, we've got 0.8 to 1.2 ppm. And then I'll just go ahead and fill in what we would see on the table, and then I'll give you the actual values, and we'll see how they are aligned. When I get to the vinylic area here, remember that this was the CH2, okay, versus the CH. So these two signals we would expect to be farther upfield or to the right relative to HC. And that's also shown on your table here, right? So let's find, we've got the vinylic where it's a CH2, 4.6 to 5.0. 4.6 to 5.0 ppm. And then the second vinylic here, that's the CH, right? 5.2 to 5.7, 5.2 to 5.7 ppm. Okay. And then if I take the proton NMR spectrum of this compound, I'm going to write in black the actual values, and we can make sure that they are what we expect them to be. This one is 4.2 ppm. Okay, so it is a little bit upfield of this range. Does that mean it's wrong? No. So this is what I mean by students sometimes going like, well, this is outside of the range, it can't happen. No, the table is just a guideline. Okay. All right, what about HD? That one is actually 4.0 ppm. And if you're wondering, are you expected to be able to say between these two, which one is farther upfield or downfield? No. But I would expect you to tell me the difference between this chemical shift versus this one. This one we expect to be farther downfield compared with these, okay? And it is at 6.5 ppm. So again, this is an example of, well, is this just wrong because it's outside of the range? No, it's not. And by the way, this is, we would expect to be the farthest downfield signal, which was both by our estimation and it matches up with what we find experimentally. Okay, let's continue on. So what about these? This is actually at 4.5. Whoops, that can... Oh, we did something wrong. Oh, there's a good learning lesson here. Okay, so this is a methylene group, right? So this is like, we're gonna learn. Yay, teachable moment. So is this just a methylene group? What is it attached to here? This is an oxygen. Oh my gosh. So it's an ether. So it doesn't belong in this range, right? That oxygen, electron withdrawing, it better be farther downfield. Notice as soon as I started writing the 4.5 ppm was like, whoa. So that would be an example of where it's like, that is way off, way off. So something was wrong and something really was wrong. Okay, so let's come over here. Hopefully I have ethers on here. I do. So I have here ether or alcohol, and 3.3 to 3.9 is the range. I'll write that down. 3.3 to 3.9 ppm is what it says on the table as the approximate range. So this, again, this is very close to that upper end. And since it is then next door to the carbon double bond, that would be one way to rationalize why this is a little bit farther downfield than what we see here in this range, okay? And similarly, with this example right here for this proton, how you're like, well, this is much higher than this. Well, it's not just a vanillic proton, it has next door to it an ether, okay? All right, good, so that was exciting. Let's try something else. Let's see, we answered it. Farthest downfield was this signal, farthest upfield was this signal. Excellent. Okay, so let's move on then. So the third, we've been through the number of proton environments, that's the number of signals or number of absorptions. We've looked at chemical shift. So the third important feature in a proton NMR spectrum is the intensity of the signal, or the integration, the area under the signal, the area under that curve, if you will. So this tells us the number of hydrogens that give rise to the signal. So if we go back, I think in the last video maybe, we looked at methyl tert butyl ether. I'm just gonna pull out, happen to have here, the proton NMR spectrum for methyl tert butyl ether, and let's just remind ourselves about that. So we have a methyl group, and it's an ether, and then we have a tert butyl group on the other side. So last time we said that there were, I'll call this A, and B, that we had two proton environments, okay? So all of these are equivalent to each other, and then these are in their own environment. And then we expect, so where do we expect this one to be? Okay, so it's a methyl group, and I won't screw this one up this time. and it's connected to an oxygen. So it should be in that ether range. And I think that ether range was, let's see, 3.3 to 3.9 ppm. And then these are also methyl groups, but they're not as close to the oxygen, right? So I'm going to go ahead and write down the primary alkyl groups are supposed to be from 0.8 to 1.2. This was, again, the primary alkyl, okay, for a methyl group, right? With the understanding that next door, so from its carbon going over, I'm going to say here plus ether, right? So I'm going to expect the chemical shift for these protons to be a little bit farther downfield than what we would expect here, but not nearly as downfield as these. So these should be the farthest downfield, and these should be the farthest upfield. Okay, and sure enough, when we look at the spectrum here, we see this signal is from these protons, and this signal is from these protons. So let's see, this is 3.5, so this looks like it's close to 3.3, okay? And over here, if this is 1.5 and this is 1, this looks like about 1.3-ish, okay? So that works out. Now let's compare the area under each of these signals. I didn't write down the integrations for you, but since we know the structure here, if this is 3 to 9, so integration of 3 to 9, this is divisible by 3, this is divisible by 3, so I could also write this as 1 to 3. So since these are both singlets, and we'll talk about multiplicity soon, this line here, the area underneath this signal, is 3 times as big as the area underneath this signal. Okay. So the area underneath the curve is proportional to the number of protons making up that signal. Okay, so that's how we can figure out the number of protons that give rise to the signal. Now, I'm not going to give you practice with proton NMRs where you're given the integrations, but I will give you the integrations on the exam. How will those look like? So for this problem here, what I could do is above this signal, I could write 3 H's. And above this signal, 9 H's, okay? Or I could do 1 to 3, okay? All right, so usually you'll notice that I don't focus much on intensity of the signal or the integration. And that's because honestly, when you take a proton NMR, you're having the computer do this for you, okay? So it's in the old days, we would bring rulers to our exams and be measuring out the heights of the peaks. And in the laboratory, before that you could do it on the computer, you would literally cut out the signal and weigh it. And so you'd weigh all of the signals like on paper and then figure out the integrations. And that's a little extreme. I'm not gonna have you do that. So we're gonna move on and talk next about multiplicity. This comes up as a result of something called spin-spin splitting, and I'm not going to explain where this comes from until the next video, so bear with me if you're like, why do signals split? We'll get to that in video number 4. So sometimes peaks are not just like those pretty singlets that you just saw in the methyl tert butyl ether example. Sometimes you'll see a proton NMR where this is one signal and it is split up into 3 peaks or 3 lines. This happens to be something called a triplet. So we need to investigate how to predict how a signal splits, what the multiplicity is. So To do that, we're going to start off with some simple examples where we use something called the n+1 rule, where we take the number of non-equivalent protons that are on the same carbon or the next door carbon, an adjacent carbon, and add 1 to it, and that tells us how many lines the signal for that proton or protons gets split up into. Okay, so the splitting or the multiplicity is the number of peaks that are in the signal. And let's just dive in with an example here. So we have an alkyl halide. First of all, question number 1, how many proton environments are there? So this I'm going to label as A, this I'm going to label as B. Okay, next we would say, okay, what would we expect the chemical shifts to be? We'd look at the alkyl halide. We've got alkyl bromides going from 3.4 to 3.6 ppm. Could we say between these two, which signal here would be the farthest downfield? Well, we've got 2 bromines attached to this carbon and only 1 attached here. So we expect this to be the farthest downfield. Since that proton should be the most de-shielded. And then this one here should be the farthest upfield. Okay, in terms of the intensity of the signals, well, we would have a ratio here. There's just 1 of these to 2 of these, okay? So a 1 to 2 ratio. What about the splitting? So this again is where we're going to use, I'm going to write down, calling it the n+1 rule. That's a 1, not a 7, sorry. So a peak, I should say a signal, let's do that. A signal for a proton or group of equivalent protons is split into 1 more line than the number of neighboring H's. So this doesn't always work, and I'll show you examples of when this doesn't work, but it does work for alkanes, alkyl halides, alcohols, and ethers. So let's try this on an alkyl halide here. So we want to predict the multiplicity of the signal that these 2 protons produce. So to do that, we go next door. So this doesn't have any protons on it, but here we have protons next door. There's just 1. So we have 1, that's our n. And then we add 1 to it. So 1 plus 1 is 2. So we expect to get 2 lines in this signal. 2 lines in a signal is referred to as a doublet. So I'm going to say here 2 peaks equals a doublet. And I'll show you what that looks like in a minute. All right, what about the multiplicity of this signal here? So going next door, so this is the carbon it's attached to. Next door to it is this carbon, and it has 2 hydrogens. So N here is 2. 2 plus 1 is 3. So this gets split into 3 peaks. And that's called a triplet. Okay. All right, so that's, let's take a look at, I'm gonna make a table for you to show this. So let's take a look here. We're gonna fill in this table. And let me get the appropriate pen here. So if we look at, I've written out the number of non-equivalent neighboring hydrogens. Okay. And so if we have 0 neighbors, n plus 1 is 1. And so we're going to get a singlet. So in methyl tert-butyl ether, we have 2 singlets because they both have no proton neighbors, okay, immediately next door. So that ratio then, if you just have 1 to start. So what does it look like? Well, what you've seen, a singlet, okay? If you have 1 non-equivalent proton neighbor, 1 plus 1 is 2. That's going to be called a doublet. And I'm going to make a little Pascal triangle here. So we'll have 2 lines, and it'll look like that. N plus 1 is 3, so a triplet. Okay, here we go. So with our signal here, what you can do to figure out the ratio of the height of the peaks is you're going to take 1 plus, sorry, you're going to look above here. 1 plus 1 is 2, and then this is a ratio of 1 and 1 here. So it goes 1 to 2 to 1. So that means that the middle, I'm going to draw my triplet, this has to be twice as high as either side. And I could be really anal and get out a ruler, but I'm not. But here's your triplet. Okay. 3 plus 1 is 4, so that is a quartet. So the ratio there, and if this ratio business confuses you, don't worry about it. I'm never going to ask you about the ratio on an exam. I'll expect you to be able to tell me this and this based on this. Okay. And sometimes I ask you, what is the number of peaks? So n plus 1, that's the number of peaks that you see. Okay. But I will not ask you to reproduce the ratio. The ratio is my cheat sheet way of remembering when I draw this out. So if this is 3 tall, and then it's going to be just 1. So it's a ratio of 1 to 3 to 3 to 1 in terms of the height of those lines. Okay, 4 plus 1 is 5. So that is a quintet. And by the way, if you're abbreviating these, I'll give you sometimes I'll write S for singlet and D for doublet and T for triplet, but then you run into, you can't just use Q for quartet because quintet also starts with a Q, okay? But just since these are some really common multiplicities, sometimes I abbreviate it. And so S, D, and T are there's corresponding meanings. Okay, so what do we have here? 3 plus 3 is 6. 3 plus 1 is 4. Let's see, 1 there. 4, 1. So we can keep going with the middle peak here. I'm going to just draw this over here. So if this is 6 high, then this one is going to be 4 high. And this one is just 1 high. Okay. So in a, I'm sorry, these are getting kind of messy. That's your quintet. Notice that if you have an even numbered multiplicity, this was our quartet, you have 2 lines in the middle matching up. And if you have an odd number, there's 1 line tallest in the middle. So that's like a quick way of going odd, even, odd, even, odd. All right. All right, so we can keep going with this. I'll just fill this in, 8, 9. So after our quintet, if we have a multiplicity of 6 peaks, that's called a sextet, and followed by a septet, followed by an octet, followed by a nomnet. Okay, and really after, you'll sometimes see if there are a bunch of peaks, It sometimes gets called a multiplet, especially if it's really if you have a whole bunch of peaks and it's messy. You'll sometimes see me write multiplet. Okay, let's look at, you will see examples of sextets and septets, but I can't think of an example of where we've had an octet or a nonet on your examples. So let's work some of these now. So let's take what we know so far, and again, I'll explain in the next video where spin-spin coupling comes from and why signals get split into multiple peaks, but for now we're just predicting those splitting patterns. So again, the splitting occurs between non-equivalent protons that are either on the same carbon, which is what we can see in the case of like geminal alkenes, and I'll get to those. These are geminal, but these happen to be equivalent. If this was like a bromo group down here instead of a methyl group, then these two wouldn't be equivalent, and then they would split each other. Okay, let's look at this example here. So question number 1 is how many signals? So how many proton environments? This is proton environment A. Well, this is also proton environment A. So there's just one signal. So remember, for splitting to occur, the splitting has to be on non-equivalent protons. These are all equivalent. So this means that there's no splitting, okay? So you have just one singlet, okay, in the range of your alkyl chloride. Let's look at the next example. So here, how many proton environments are there? How many signals are we going to end up with? Well, I see here, if this is my methyl group here, is being A. Well, this methyl group is also in the same environment. Okay, no protons here, but we have protons here, so that's B. So we have 2 signals. Okay, and then we would expect this one to be farther down field relative to these, right? And then in terms of the splitting, so for signal A, has 0 proton neighbors. So signal A is going to be a singlet. And remember, that one should be the farthest upfield. This one should be the farthest downfield. And when I say farthest downfield, I'm not talking like 10. I mean, this is still not going to be very far downfield, but it'll be more downfield relative to signal A. So for signal B, how many neighbors does it have? Well, 0 proton neighbors here. So it's also a singlet. And its signal will be farthest downfield. Ooh, let's do the integrations. So signal A should integrate for 3 plus 3. So 6 H's is the integration. Whereas signal B integrates for 2 H's. So this could be reported then as a 1-to-3 ratio. So the integration ratio is 1-to-3, right? Okay. Let's do this one now. So here we have a plane of symmetry here. So HA, HA, HB, HB. So we have 2 signals. These have no proton neighbors. So signal A is going to be a singlet. Signal B also has no proton neighbors. Okay. So also a singlet. No splitting. Well, that's convenient. Okay. So let's see if next time I can give you some examples. Let's just do one now. let's squeeze it in here. So let's change this. Let's make this BrCH2. Let's have the neighbor CH, BR, BR. Did we already do this one? I don't remember. Okay, now we have two signals, 1, 2. Splitting for A, its neighbor has 1, so 1 plus 1 is 2, so this is a doublet. Signal B has 2 proton neighbors, 2 plus 1 is 3, so it's a triplet. Okay, this signal will be the farthest down field. This one will be a little farther up field. Okay, all right, so in the next video, we're going to take a look at why the spin-spin splitting occurs, and we'll learn to draw the splitting diagrams given coupling constants, so stay tuned.